Swayam Prabha. Digital India. Educated India.
Okay, welcome back. This is a new chapter, stresses in underground opening. Okay, this is a very important chapter for mining and geotechnical engineering students or rock engineering students. This is where everything starts, other than your the relationship between stress, strain, and porosity, whatever we have talked about, these material properties. Now, actually, how does the stress, behave in underground? That you will get to know. So this is a picture of in situ stress ratio versus depth, or I would say the depth versus in situ stress ratio, whichever way you say. Now, most probably, Professor Varma has told you that the in situ stress ratio K, which is a mean horizontal stress divided by the vertical stress. So that's a very important parameter for us. Okay, this parameter, if I can get it. Today network is little slow, so everything is opening very slowly. Okay, so you see this, all these points which are given here. All these points which are showing here, and you see the depth, it is about 500 meter, and you see the ratio varies from all the way to 5, even 6 to somewhere 1 also. Okay, so the concentration is somewhere around this zone, right? And this is, you can see, about 200 meter zone. So what it tells us, if you go 200 meter below, the stress ratio K is more than 1, right? So the horizontal stress is more than the vertical stress. Okay, can anybody tell me why? Because I think Professor Verma must have taught you already in situ stresses. What is the formula? We know. If you remember, this K is nothing but nu by 1 minus nu. This is the Poisson's ratio, right? He must have told you that sigma H is equals to nu by 1 minus nu sigma V, and I proved it in one of the classes. Now, if you see the value of nu, the Poisson ratio, this value is basically 0.25, 0.25 by this is a difficulty in writing here, 0.75. So this basically gives us 1/3. Okay. So what we are saying here is this horizontal stress, according to this formula, is 1/3 of the vertical stress. But actually, this is the tested data in the field and all over the world. This is not for India. Even I don't think Indian data is here. This is all over the world. You can see in a shallow depth, less than 500 meter, the concentration is such that the point concentration is such that it is more than 1. And if you plot the average thing, then this curve will be something like this. This is the average graph. So it is highly more than 1. Now, any of you know why it has happened? because this formula doesn't support it. This said it should be 1/3. Okay. And if you see why it is 1/3, if I go below down, you see the K value is 0.3. When you are 2.5 kilometer below, you see here. But our mining zone is more or less, let's say 1 kilometer. So in the 1 kilometer, even the median one is not coming to be 0.3. Okay, so I wanted to show you this graph or this plot so that you understand what is happening. Okay. Now we are in a stress field, something like that. Now I'm not sure whether Professor Verma has shown you how does the stresses looks like in the field if there is a fault. Okay. Fault. Do you know what is fault already from geology?
Yes.
Define it for me. Just one of you, anyone. What is a fault? How do you define it? If they gave you definition in geology, if he has not given, you ask him.
It's a type of discontinuity. A plane having uh, there is a movement.
Yeah, there is a movement. Correct. This is a plane of discontinuity caused by what?
Tectonic movement of plates.
Okay. So plate tectonics, from plate tectonics is defining it. But fault can happen. Those are big faults. Like we have one in Nepal area. Okay. This is the Indian plate and the China plate. Those are, not only we are in Ladakh, these plates are also on top of another. Okay. They are also pushing each other. Um, so those are big plates and big faults, but there are many local faults. Okay. And they occur due to what? Tensile failure or compressional failure, by which method? Okay, if we didn't tell you, because it's not a geology class, so you can ask him. Now what is happening is, you ask him how does the fault form, okay, locally, not those big ones. Because when you go to mine or you go to any place, you will see a small fault or a small fold. Okay. Now, in a near the fault, why I'm saying all this? Because you should have a feeling of stresses. So the difference between the mining engineering and any other engineering is here. Let's say I give an example of civil engineering. They make a bridge. Okay. Now what they do? They estimate what kind of stress can come. That means how many vehicles can be there at one time. And there may be a wind load, which may be dynamic. And then they design the pillar, if they have to put pillar in between. So what will be the size of the pillar? What will be the material property of that concrete they are going to make? What kind of rod they are going to use? What will be the diameter? Based on calculation of those loads that may come on that bridge. Okay, that means after the structure is made, the stress will come on it. Okay, this, you think of any engineering branch, this is what it is. After the product is made or a structure is built, then the stress will come. In mining engineering, the beauty is stress is already there. Okay, we call them in situ stresses. We are going there to disturb it. Okay, this is the difference. And we have to know how much to disturb so that we are safe, or the person who is working under you are safe, because you are responsible to send him to get coal or mineral or ore from that place. So there is a fine balance between that in situ stresses and the kind of geometrical shape you can create under the prevalence of that stresses. So if you do not have that understanding, you are bound to go for failure. And that is this chapter is all about. What is the relationship between shape, size, and the stresses which is prevailing in underground? So one is this K. K factor is very important. So we must understand how does it, vary or behave with depth, or as we are going deeper and deeper, how does this stress changes, and then what kind of geometry we can create to get that ore out. Okay, finally we have to create some void because we have to extract the mineral. Another difference between another engineering field and our engineering, that is mining engineering, is they build a structure by construction. Okay, remember that always. They build a structure by construction. So when they build a structure by construction, they know the construction material very well. If they do not like that material, they can throw it out and get a new material which is suitable. We build structure by extraction. So we cannot change the material property. Okay, there is no way. The mother nature is already given us that material, that coal, for us to extract. Now, if you see the difficulty in extracting that coal, you cannot tell your boss that, this is a very difficult thing, I cannot do it. You have to find a way to get that mineral. If there are some gold deposits somewhere, but material is very weak, you cannot say, I will not get that gold. You cannot say that. We have to go out there, get that gold out safely. So for that, what do we need to do? So all this understanding is very important. Okay, what I'm going to tell you in this chapter. So if there is a fault, this is just for your information. We will not going to use in this class the fault analysis. So for a normal fault, which you know, definitely this sigma V will be the maximum because it is pushing the hang wall down. Okay, this is we call hang wall. This is the basically hang wall, and this is we call foot wall. So it is pushing the hang wall down. So sigma B should be the highest, and that is your sigma 1, the maximum, or the major principal stress. Now for a I come here for a thrust fault or a reverse fault also it is said. Now here definitely this sigma H, which is pushing it up along this. So this should be the sigma 1. This is becoming my sigma 1. Okay. Now for the strike slip fault, which the fault is towards the strike, there is also sigma H is maximum. This is also sigma 1. Okay. Sigma V is in the middle and sigma H is very, very minimal. The other side. Okay. Very, very minimal. So this is sigma 1 here for a normal fault. So whenever there is a normal fault, that means hang wall is going down. So you will know sigma V is my sigma 1. But if it is a thrust fault, that means sigma 1 is more than that means horizontal stress was more. That's why it has went up. Then sigma H min and then sigma V. So accordingly, we have to understand that what is the value of K I have to take. Okay. So this is what should be the understanding if there is a fault. Okay. Now I show you another picture and then we will go to the whiteboard and we'll do the work. Now you see, this is a picture of a tunnel. This one, the right hand side. I hope you can see. It's a more or less circular tunnel with lining is already given. The concrete lining is given. So now, if I take a section, okay, along this, I will see a section like this, circular opening. So there may be a P naught, which is probably, let's say, acting like this. This is probably P naught, or you may say anyone. This may be a sigma 1, okay, and or it may be sigma V. It doesn't matter, and this may be sigma H if you are comfortable with V and H symbol. So that is the horizontal stress, and this we are representing by K P naught, because this is what is K into P naught, and K is that ratio. Okay, the ratio between horizontal stress to vertical stress. Now there is a person called Kars. Now here another assumption I am going to tell you. What we are trying to find out, what is the difference between in situ stress and induced stress. Now, let me tell you this. Let me draw here only. If there was no tunnel here, then the stress should have passed directly like this. There is no tunnel, stress should have passed directly like this. You studied magnetic material, behavior of magnetic material. So let me just draw something here. Let's say this is two magnet here, N and S. If there is air here, there is nothing here, how does it go? It goes something like this, right? Your magnetic lines, you have studied them in your class 12. It goes like this, right? Anybody, you have done these experiments? Now, you tell me this. If I put a magnetic material here, 1 minute. Okay. If I put a magnetic material here, means which attract the magnetic field, how does the line will go? Can anybody tell me?
Will it pass from the material?
Yeah, it will pass through this, and with high concentration, right? With high concentration, it will pass through this. And if I made a non-magnetic material, let's say I erase this. Now I put a non-magnetic material here like this. Then how it will pass? This will go all the way. It will bypass this, right? isn't it? It will bypass completely that non-magnetic material. Let's say wood or something I put here. So the line will bypass it and come like that way. But there will be nothing will pass through this. Okay. Now similar thing is here. When if there is no the tunnel, so I have a material here. So it will the stress line or the stress potential lines, whichever you think, will pass through this completely because there is a solid material. Now I told you I used a word called disturbed. I have disturbed these stress lines which was already existing there by making a hole. We call it tunnel or any other, maybe mine gallery, okay, or a stope by extracting the mineral from a stope, okay, or from a panel, whatever. Now, when I have done that, I have disturbed these lines and I made a vacuum, and stress cannot pass through vacuum. And as a result, the stress will pass through, bypass it, and it will go something like this. If there was a horizontal stress, it will also pass like this. Okay, it will bypass that. So this is the disturbance, what I was talking about. Now the question is, how far is that disturbance? Okay, this we have to know. And how much is the disturbance? That is also we have to know. Okay, what is the intensity of it and what is the extent of it? How far it will be and how much it will be. Okay, to investigate that, a person called Kars, let me delete all this. Even I think in 1856, if I am not mistaken, I didn't write the date. I think right around in 1856, he has developed a solution. Means what could be the stresses? And that is a very, very famous equation, not only for mining engineering, for mechanical aerospace, for everybody. Okay, anybody in engineering field, we normally use this equation. Okay. Now, what he has said that if this is a circular opening, this is what he has told, for a circular opening of radius A, and stresses are like this, P naught and K P naught. Mind that there will be no shear stress. Okay, there is no shear stress. Okay, so it's only the normal stress what we have here. Now, can you tell me then what is this plane we are discussing? A plane which doesn't have a shear stress. What is that plane we call? Principal plane. So he has developed the solution for principal plane. Okay, there is no shear stress here. So only P naught and Kp naught. Okay, normal stresses. And that is in the far field. This is what is in situ stresses. Remember that these are in situ, which is pre-existing. So this may be far away from that hole or from that circle or the circular tunnel. Then he said at r distance apart from the center, having an angle theta here, and we have three stresses here, sigma rr, which is in the radial direction, sigma theta theta, which we call, this is the sigma theta theta, and radial is in this direction. So this is we call sigma rr, this is sigma theta theta, and there is a shear stress here. Okay, this is tau r theta. So these are the three stresses. New stresses will form. Okay, that is what he said. And he has said what will be the formula. In the book, we have derived that formula. It is given in the appendix. So if you are interested, you can see that. But in this class, I'm not going to discuss the derivation. Now, these are the following assumptions. What are the assumptions? That there is no shear stress. Hence, it is the principal plane. Third principal stress is acting along the tunnel axis. So this is perpendicular to this plane along the tunnel axis. And the density of this rock here, okay, that has been ignored. It is not there. Okay, these stresses are so high, we can ignore this density, at least in the influence area of that circle. Okay, so far you understood the concept by which Cars has given or solved that equation, right? Now I go to the whiteboard. I hope you understood this part. So I'm going to now share the, let me draw it here so that oops. So this is what is P naught and this is what is KP naught. Okay. And circular hole is here with some radius A. Okay. Now the solution which he has given, you can write it down also. So sigma RR, that means if I have a small element here, the stress acting like this is our sigma RR. So you can write this stress. Let me shift it a little bit this side so that I can write. Sigma RR is P naught by 2, 1 plus K, 1 minus A square by R square. Okay, minus 1 minus K, then 1 minus 4 A square by R square plus 3 A power 4 R power 4. This entire thing cos 2 theta. This bracket close. So P naught by 2 is multiplied by the entire thing. Okay. This is sigma RR. That is what he said will be. Now sigma theta theta, that means in this direction, stresses, the normal stresses will be. Now what is theta? Going counterclockwise from the horizontal. And this is the distance r. At r distance and theta distance, this is given in polar coordinate system. Okay. Now sigma theta theta, I use this. Similar like this, 1 plus K, only thing here is 1 plus A square by R square. Okay. Then here it is not minus, it is plus 1 minus K, 1 plus 3 A power 4 by R power 4. Okay. And this cos 2 theta remains the same. This is that we call it tangential. This is we call radial stress. This is called tangential stress. That is radial stress. This is tangential stress. Okay, and another is shear stress. We will write it here, tau r theta. And this can be written in any form like this. So tau r theta will be P naught by 2 again, 1 minus K, and then 1 plus 2 A square by R square minus 3 A4 by R4. This will be sine 2 theta. Okay. This is the stresses which is given by the Cars in 1856. Okay, so you see, this is a very important. These three equations are very important, and not only mining. I'm telling you, in all engineering branches use this formula. Okay, this is basically the induced stresses. This sigma RR, sigma theta theta, and tau r theta are the induced stress developed because of this circular hole. And you can see how it is relating to in situ stress. This is my in situ stress, and K is also my in situ stress. Means in situ stress parameter. Okay. So how the induced stress is related to in situ stress, he has shown us this. Okay, now what do you understand by this equation? Okay, that is more important to us. Then how do we derive? Because he has derived it more or less 170 years ago. So this must be right. But what do we get? First of all, you see, this is a highly nonlinear. That is what it looks like. Because it's you can see it's related to r to the power 4. So what it tells us, the little bit movement of r means if you go away from that hole, the stress will change very drastically, not linear. It's a very significant drop will happen, drop or increase, whatever will happen. All the three components. So that's a very important thing. And another is that it's also related to theta in both in two theta terms, not in theta terms. So you can see it is more or less that Mohr circle type of thing concept is coming here also. Now another important thing, what we are finding it here, if K equals to 1, okay, if K equals to 1, okay, I hope you have noted down this equation because I'm going to use this very much. Now, if you see if K equals to 1, what is happening in this equation? What is happening? Can anybody tell me?
Shear stress will be 0.
Shear stress is not there. Great. Anything else? What happened in the this term, 1 minus K term, that goes away. Okay, that means this is no longer theta dependent. See, all theta term gone the moment K equals to 1. Okay, so there is no theta dependency if K equals to 1. Okay, that's great. Now, what do you mean by K equals to 1? What it means, K equals to 1?
Principal plane.
No, no, principal plane, okay, because tau r theta is vanished. That is also principal plane. That I agree.
Mu is
Huh?
equal to 0.5.
So the stresses will be equal. So the stresses of
No. Do not go by that. It's this K also has many other things. Not only that mu by 1 minus mu. Okay, that may have a tectonic part, that may have many other frozen stress part. I hope Professor Verma has explained you all those. It's K equals to 1 means sigma H is equals to sigma V, right? This
isotropic.
means sigma H is equals to sigma V. That means horizontal stresses are equals to vertical stress. That means at that point, wherever you have you want to construct that tunnel, the stresses in all directions are same. Where does it happen? In which condition does it happen?
Hydrostatic condition.
Hydrostatic condition, correct. So it is basically, we call it a hydrostatic case. Means what she said, no, the mu equals to 0.5, but here we will not say mu equals to 0.5. Mu may be 0.25, it doesn't matter. There's something else is added to that horizontal stress, and that made it same as vertical stress. So that's a very important issue. So if sigma H is equals to sigma V, then theta dependency is gone. That means the stresses doesn't depend on angle, only depend on R. Okay, this is what it tells us. At least this equation tells us. And also another thing, tau r theta vanishes. That means even this small element, what we have done here, this is also in principal plane. The stresses also stresses applied in a principal plane, and the stresses which is developing inside that rock is also principal plane. Okay, so that means the induced stress is also in principal plane. So it's a very special case, and we first analyze this particular case. Okay, now what happens? You have written this. Now I will now show you. I'll go back again and I'll open another file. Are you able to see this Excel file? Two graphs.
Yes.
Here it is visible, right?
Yeah.
Okay. I'm not sure how many of you know Excel, but today I'm going to tell you a little bit how to plot this complex, this equations in Excel very easily. I make K equals to 1, and see the problem is here. This is a problem from the book 7.1, and what it says is there is a horizontal tunnel, and in that horizontal tunnel the P naught is applied as 14 MPa, and the values are given such that the K become 1. Okay, just I have given like that way so that you can do. So we want to find out the at theta equals to 0 degree. It doesn't matter though. That's why I'm showing you. If theta equals to 0 degree, then the tunnel radius is 2 meter. Tunnel radius is 2 meter. Then what is the sigma RR and sigma theta theta? This is sigma RR and sigma theta theta. What is these two values? Okay, so I have just plotted it. Now, how I plot? This is the equation. Okay, I can click here and then you may see. See, this B2 is nothing but P naught by 2. You see this, the entire that equation I have written here. Now only variable is R. Okay. If you do not know how to use Excel, You just learn it, it's very easy. You have to just type that equation depending on the cell. So when you say B2, here $B, $2 means this will fix this number 14. Okay. And the variable is A7. So you do not put dollar anywhere. Baki, you can see the equation is 1 plus B1. So that is this one, K, this value. This is the value 1. And that equation has been written with the theta also. Now, when you use in Excel or any computer program, you know theta has to be written in radian because that is what they understand, the compiler. They do not understand theta, degree. So I have converted into radian also. If it's 0, it will be this. So you can see this is just, you have to write radians. This is already a function written in Excel. It's an inbuilt function. You don't have to do anything. Radians B3 means this one. So it will return as a radian value of that. Now, then I have plotted here. I have gone R. R equals to 2 means what? R equals to 2 means right at the boundary, right? You understand? Because my A is 2 meter. So when I'm given R equals to 2, this is on the boundary I'm giving. So that's why I've given also R by A, so that we know where it is. And after that, it is going into the rock. So 2.53, 3 meter, 3.54 and all this. So it is inside the rock. And SRR is your radial stress for this R. And this is the sigma theta theta. And that is the tangential stress. Now these become 14. Okay. Now after that, if you go 2.5 meter below, so that means what I am plotting here is, let me plot it with 1 minute. Fine. So what I have plotted is the R by A with these two. Now this upper one is tangential stress, and this lower one is radial stress. Okay, and you see they are converging right around 14, right? You see the 14 is somewhere around here. So it is converging towards 14, both of them. Now, can anybody tell me why it is converging towards 14? What is so important about 14?
It tending to in situ stress.
Yes, it is going towards the in situ stress. So the blue one is my radial stress. So why the radial stress is 0 right at the boundary? If you see the equation, you will know, because there A is R is equals to A. So all the term becomes 0. Okay, because K is also 1. So the theta dependency is not there. And since R is equals to A, so the entire term becomes 0. That means there is no radial stress in a free boundary. We know. In a free boundary where there is no material, there will be no normal stress acting in that boundary. Okay. So the normal stress is 0 at a free boundary. So that's why it is 0. But you see this value. This is very interesting. This become double, 2 P naught. Okay. Now the sigma theta theta right at the boundary is becomes double. Now if you see again in the equation, this is 1 plus a square by r square. So it become 2 because r by a is 1. So it become 1 plus this square. So it basically 1, it become 2. And there is no theta dependency. So that's why these become double. Okay, so it used to be 14. Because I have created a circular tunnel, I have disturbed the stress doubly. So the the radial stress we made it 0, and the tangential stress we made it double, where both of them used to be 14. If I would have not excavated that area, both of them 14, and they are happily ever after. There will be no failure. Now, one I have made 0, another I have made double. Okay, because of the tunnel. So this is what is the disturbance I am creating. Now, as you are going inside, you see how quickly it is falling down and how quickly it is rising. Okay, the blue one is quickly rising towards 14, and the tangential one is quickly falling towards 14. Now, here quickly mean I have gone up to 9. Still, I should have gone up to 10. Then it is 5 times. But you are seeing the trend, it will go towards that only. Say one is becoming 13.3, another is becoming 14.69. So very quickly it is falling down. So you understood this part. Now why I'm doing this, I just want to show you. If I put here 90 degree, see no change. Even if it changes the the degree, but actually there is no change. Okay, actually there is no change because theta dependency is not here. Now you see the theta dependency. I again put it 0. Now this I made, let's say, 0. Meaning what? There is no horizontal stress. I'm assuming there is no horizontal stress. Sigma h is 0. You see how does the curve change? And you see where it has gone. This become 3 times. Okay. So if the horizontal stress is very low or close to 0, the moment I create a tunnel, my tangential stress is 3 times the in situ stress. Okay. So we have to know whether that particular rock can sustain this much of stress, because that has a strength. Okay. Whether it can take that much of stress, we have to know. And then it is gradually, it quickly falls, and then you see the behavior of this. It quickly rises, but since actually there is no horizontal stress, it is again going towards 0. Okay, the horizontal stress again going towards 0 because actually there is no horizontal stress. So it is quickly going towards the again in situ stress, and it is coming towards 14 already. You see, this is coming towards 14, and that is coming towards 0. Okay. Now you see, if I give any other value, let's say if I make it double, horizontal is, oh, okay. Let me show you this. If this is 90 degree, this is very interesting. If I give 90 degree, what happens? You see, if I give 90 degree, this become negative. My tangential stress become negative. Can anybody tell me what does it mean? At 90 degree, right on top. This is actually, sorry, this is actually not tangential stress. Now this is my radial stress become, because it's 90 degree. But what does it mean, this negative? Is it wrong? Cars is wrong. Suddenly came negative. Can anybody explain that? What is that negative stress mean here?
It changes its direction.
Yes, meaning what? It become tensile. Okay, I'm going to now just within next 5 minutes. I will take another 5 minutes, and I'll draw it for you. Then you can understand. Now you just see the behavior, and this was 0, and then going towards 40. Okay, and I show you another thing. If it is double and 0, so doubled and 0. So this will double means horizontal stress will become twice. Okay, see, this is going towards that 28. Okay, and this was coming towards 14. Well, horizontal stress is now double. So you can see that. Now I go back to the whiteboard. Okay, now I'll draw it for you. What you have just seen. What are the what they mean? Okay, the first case k equals to 1. The way we have seen, this is at theta equals to 0 we have plotted. So right here we have plotted, this was our tangential stress, this was the double 2p naught, and the radial stress and tangential stress. This is how it has gone, and this was p naught. This happened at k equals to 1, right? Now I have shown you one k equals to 0, and let me show you what happened, why that negative came. So let me delete them. Now at theta equals to 90 degree, so it is like this, theta equals to 90 degree, right? This is what is 90 degree. This is my theta. Okay. 90 degree, what happened? You have seen this stress, this directional stress. Okay, it went, let's say I plot this side positive and this side negative. Okay, so this has happened something like this, and then it crossed and something like that happened. So in other words, here a element was getting stresses like this. So right on, you can see a worker will be standing here. Okay, or a person or a vehicle, whatever, will be going like this. Now on top of this, the rock elements are in tension, so a crack can generate here very easily. So we have to understand what is the behavior of stress and how much stress it can generate, and whether the tensile strength of this rock can sustain this stress. We have to also understand that. So that is what has happened at k equals to 0 and theta equals to 90, and this is a very dangerous situation. See how the in situ stress changed. Okay, due to just making a circular opening, I completely disturbed the stress. Okay, now I again explain you with k equals to 1. Let me draw it again, otherwise. So what happened if I take an element here we have seen at K equals to 1, these become 2 P naught. And this direction is 0. This becomes 0 right at this boundary. Now, if a element is here, this has lowered down and this has increasing. Okay. So what is happening is right here, what we call it is like a UCS test. Just unidirectional stress is active. And here rock may fail. Okay. It may crack. But if you go a little bit inside the rock, we have good confinement. Okay. The rock is being held by this sigma RR. Okay. So we have good confinement stress and the breaking stress or the tangential stress or the failure stress, whichever way you name it, the intensity is also reducing. It is going down. Okay, it is going down. So there is a less chance of failure as you are going inside. That means you are going towards the in situ. So as we are going there, we are going towards in situ. This side is basically induced side. You can say induced, and there will be a particular zone after which they are very close to in situ. So we call this particular zone around this is the influence zone. Okay. So when I create or I construct a tunnel in underground, I have to know I'm going to disturb the in situ stress. And I'm going to create an influence zone of that tunnel until it again comes very close to in situ. Now in the next class, we are going to discuss about that influence zone, how far we can for all practical purpose, we can say the zone of influence is gone. After that, it is same as in situ. Okay. So now you see this is what is the beauty here, that as it goes inside, confinement increases and tangential stress reduces, and as a result, it is very quickly go towards the in situ values, whatever they are in before. That means P naught and K P naught. Okay. So I will stop here. Let me do not go away. I'm just stopping the video recording.